far from the warmth of the inner planets. Neptune moves through a region where sunlight has been thinned by distance. From there, the sun no longer dominates the sky as it does from Earth. It appears smaller, sharper, and more remote, illuminating clouds, rings, and moons with only a fraction of the light that reaches our world. Among those moons, one is unlike the rest. Triton is the largest satellite of Neptune, a rounded world of ice and rock, about 3/4 the diameter of Earth's moon. It circles its planet once every 6 days, but it travels in the wrong direction. Neptune turns one way, Triton moves the other. No other large moon in the solar system follows such a retrograde path around its planet. That reversed orbit is more than an unusual detail. It is a surviving trace of an older event written into motion itself. Triton was probably not born beside Neptune. The leading explanation is that it formed much farther from the Sun, among the icy bodies of the outer solar system, and was later captured by Neptune's gravity. Its resemblance to Pluto supports that idea. Both worlds contain large amounts of ice. Both carry thin atmospheres dominated by nitrogen. Both belong, in different ways, to the cold population of objects that formed beyond the major planets. Yet, Triton no longer travels freely through that distant population. It has become a moon, bound to Neptune in a close, nearly circular orbit, moving backward through a system it may once have entered as an outsider. The capture could not have been simple. A lone object passing Neptune would normally accelerate, curve around the planet, and escape again. To remain, Triton had to lose energy. Scientists have proposed several paths by which this may have happened, including an encounter involving a binary pair of icy worlds. In that possibility, Neptune took one member while the other was flung away. Whatever the exact sequence, the result reshaped more than Triton. A newly captured body on a wide, tilted orbit would have disturbed Neptune's earlier moons. Some may have collided, some may have been thrown outward or lost. Over time, tides drew Triton inward and rounded its path, leaving the present system as the faded aftermath of a gravitational rearrangement. For most of human history, none of this could be seen. Triton was discovered in 1846, only 17 days after Neptune itself was identified. Through Earth-based telescopes, it remained a distant point near another distant point. Its true appearance waited until August of 1989, when Voyager 2 passed through the Neptunian system. The spacecraft found a pale world, marked by frozen plains, ridges, pits, and terrain unlike anything then known. Its surface was cold enough for nitrogen to remain as ice. Above it hung a thin atmosphere and layers of haze. Dark plumes rose several miles over the surface, carrying material into winds before it settled again in long streaks. Voyager saw Triton during a single brief passage. No spacecraft has returned, and much of the moon remains known only through that encounter and the patient observations made from Earth. So Triton remains suspended between what is known and what one visit could not resolve. It is a captured world with a changing surface, a thin atmosphere, and an interior that may still hold warmth beneath its frozen exterior. To understand Triton is to follow two journeys at once. One leads outward across the solar system toward Neptune. The other leads backward into the time before Triton became a moon at all. A place on Triton would not feel like a distant version of Earth. The horizon would be closer, the ground lighter beneath you, and the sky would carry a planet where our own sky carries a moon. Neptune would hang above one side of the landscape, broad and blue, nearly fixed in position. Triton keeps the same face turned toward its planet, just as Earth's moon keeps one face turned toward Earth. From the hemisphere that looks inward, Neptune would remain suspended over the same region of sky, while Triton completed its orbit. From the opposite hemisphere, the planet would never rise at all. This fixed view comes from tidal locking. from Triton rotates once each time it travels around Neptune, completing both motions in a little less than 6 Earth days. The result is a world divided not by permanent day and night, but by permanent access to the planet itself. Some places would always have Neptune overhead. Others would know it only as a presence beyond the horizon. The planet would appear far larger than our moon appears from Earth. Its disk would span several degrees across, wide enough that its shape would be unmistakable even to an unaided eye. Bands of cloud would be difficult to see without magnification, but the globe would still dominate the sky as a colored world rather than a point of light. Around it, the inner moons would move quickly. Naiad, Thalassa, Despina, Galatea, Larissa, Proteus, and Hippocamp all circle closer to Neptune than Triton does. Most follow the planet's direction of rotation. From Triton, their paths would be set against the larger disk and the faint rings, each moon crossing the system according to its own short orbital rhythm. Triton would move against that pattern. Its retrograde orbit it around Neptune in the direction opposite the planet's spin and opposite the motion of the inner moons. This reversal cannot be felt while standing on the surface. There is no wind created by orbital direction, no visible line beneath the ice marking which way the moon travels. But across the scale of the Neptunian system, Triton is continually moving through traffic that was organized the other way. The orbit is also tilted. Triton does not circle neatly above Neptune's equator. Its path is steeply inclined, a geometry that changes how sunlight reaches the moon over Neptune's long year. Neptune requires about 165 Earth years to orbit the Sun. As the planet and its moons travel through that immense season, Triton's poles take turns leaning toward the distant light. A season there can outlast a human life. Sunrise would not bring warmth in any familiar sense. At Neptune's distance, sunlight is roughly 900 times weaker than it is at Earth. The Sun would look like an intensely bright star with a tiny, visible disk, about 1/30th the width it appears from home. It would still cast shadows, it would still drive changes across the surface, but its energy arrives in a narrow, reduced stream after traveling about 4.5 billion kilometers. At certain points in the long seasonal cycle, the alignment could also carry the Sun behind Neptune. When that geometry occurs, the tiny disk would disappear completely behind a planet hundreds of times wider in the sky. The landscape would enter an extended eclipse, not because the Sun had set below the local horizon, but because Neptune itself stood in the way. The blue planet would become a dark circle with a narrow rim of scattered light, while Triton continued along the backward course of its orbit. Such alignments would be part of celestial mechanics rather than daily weather. Another reminder that the sky above this moon is governed by a captured world's unusual path. Even that limited sunlight matters because Triton's surface is made from materials that respond to small changes in temperature. Nitrogen, methane, and carbon monoxide can freeze onto the ground or pass into the atmosphere as conditions shift. On Earth, these substances are gases under ordinary conditions. On Triton, they participate in a seasonal exchange between surface and sky. The atmosphere is extremely thin, but it is real. Nitrogen is its main component, with smaller amounts of methane and carbon monoxide. Near the ground, there may be enough gas to carry fine particles and shape the dark streaks seen by Voyager. Higher above, sun's light acts on methane and helps produce a layered haze. The sky would not resemble the deep blue of Earth. There is too little atmosphere for that familiar brightness. Near the surface, the view would likely remain dark, with a faint haze becoming more visible toward the horizon, or when illuminated from behind. Neptune's reflected light might add a dim blue presence during parts of the local night, depending on where you stood and how the Sun, Moon, and planet were aligned. The ground beneath that sky would be among the coldest surfaces ever visited by a spacecraft. Temperatures measured during Voyager's encounter were near 38 kelvins, only a few dozen degrees above absolute zero. At such temperatures, nitrogen ice becomes part of the terrain. Water ice behaves less like the ice in a glass and more like hard bedrock. Gravity would also change the feeling of the landscape. Triton's surface gravity is less than half that of Earth's moon and only a small fraction of Earth's. A step would carry the body farther. Loose material would fall more slowly. Yet the moon is large enough to hold a rounded shape, separate into internal layers, and maintain the thin envelope of gas above its surface. That balance gives Triton its unusual character. It is small enough for the horizon to curve close by, cold enough for familiar gases to become glaciers, and large enough to preserve a complicated geological history. It is a moon now, but many of its properties still resemble the independent world it may once have been. Neptune's presence would make that history difficult to forget. The planet would remain above the same frozen plains, filling a significant portion of the sky, while tidal forces continued their patient work inside the orbit. Triton does not merely circle Neptune, it is tied to it, facing it, moving backward around it, and gradually surrendering orbital energy. No human has stood beneath that blue disk. Our only close view arrived through cameras and instruments, moving too quickly to remain. Yet the geometry is clear enough to imagine without adding anything to it. A pale surface, a thin nitrogen sky, a small distant sun, and one immense planet holding its captured moon in place. A different kind of journey began in the autumn of 1846, not near Neptune, but beneath the damp night skies of England. Only 17 days had passed since astronomers had confirmed the existence of Neptune. The new planet had appeared through a telescope as a small blue disk, close to the position where calculations suggested an unseen world might be pulling on the orbit of Uranus. Almost immediately, observers began searching the space around it for companions. William Lassell, an English brewer and skilled telescope maker, turned one of his own instruments toward the new planet. On October 10th, he noticed a faint point moving beside Neptune. It was too dim to see without a telescope and too distant to show any surface detail. Yet its changing position revealed that it was bound to the planet. That point was Triton. For more than a century after Lassell's discovery, the moon remained almost entirely without a face. Astronomers could follow its orbit. They could estimate its brightness and gradually improve measurements of its size. They could determine that it traveled backward compared with Neptune's rotation. But Triton itself was still compressed into a speck of light, too small in the sky for the telescopes of the time to resolve into a landscape. The backward orbit became the first strong clue that Triton did not belong to Neptune's original family of moons. Large, regular satellites usually form from disks of material circling in the same direction as their planets. Triton's motion resisted that pattern. Even before anyone could see its ice, plains, or atmosphere, the orbit was already suggesting a history of capture. As telescopes improved, the faint light began to offer more information. Astronomers separated it into colors and studied which wavelengths were absorbed. The surface appeared to contain frozen volatile materials, substances that can move between solid and gas under the weak sunlight of the outer solar system. Triton was no longer only a moving point. It was becoming a cold world with chemistry. Still, the details remained hidden. Neptune lies so far from Earth that even a large moon around it appears tiny. Atmospheric turbulence blurs ground-based views, and before modern adaptive optics and space telescopes, that blur placed a firm limit on what could be learned. Maps could not be drawn. Individual landforms could not be named. No one knew whether the surface was heavily cratered, fractured, smooth, or active. Then a machine crossed the distance. Voyager 2 had already visited Jupiter, Saturn, and Uranus when it began the final planetary encounter of its mission. By 1989, it had been traveling for 12 years. Neptune would be its last close passage by a major planet, and the geometry of the encounter was designed in part to bring the spacecraft near Triton. This required a path unlike any earlier planetary flyby. Triton's tilted, retrograde orbit carried it far from Neptune's equatorial plane. To pass near the Moon, Voyager had to sweep over Neptune's northern regions and continue toward Triton on a trajectory that would bend the spacecraft away from the plane of the solar system. The encounter could happen only once. Voyager had no engine powerful enough to stop and enter orbit. It would approach, gather what it could, and continue outward. As the spacecraft drew nearer, the old point of light widened into a disk. At first, the images showed broad differences in brightness. One region appeared pale and reflective. Another was darker and more varied. With each new frame, the surface sharpened. Features that had never been visible from Earth began to emerge. Long ridges, smooth plains, irregular depressions, dark streaks, and a southern polar cap covering much of the hemisphere presented to the spacecraft. The landscape did not resemble a simple, inert ball of ice. Some regions looked strangely textured, with rounded rises and shallow pits arranged in patterns unlike the terrain seen on other moons. Planetary scientists later gave one of these areas the informal name cantaloupe terrain because its repeated cells resembled the surface of that fruit. The comparison was useful, but it did not explain how the forms had developed. Possible explanations included deformation of the crust, the rise and sinking of ice, and resurfacing driven by warmth from within. None could be confirmed from a single flyby. Voyager had revealed the shapes, but not the full history that produced them. Elsewhere, wide plains carried signs of flooding or flow. On Triton, such movement would not require liquid water at the surface. Nitrogen, methane, and other volatile ices can behave in unfamiliar ways at very low temperatures. Materials that remain gases in an Earth room can condense, freeze, migrate, and perhaps flow across this moon. Water ice, by contrast, forms much of Triton's rigid foundation. At temperatures near 40 kelvins, it is not soft or slippery. It acts more like stone. Over that hard crust, layers of more volatile ice can respond to seasonal heating, pressure changes, and local geology. Voyager's images also revealed a surprising scarcity of large impact craters in the areas it photographed. Every exposed surface in the outer solar system is struck over time by comets and smaller debris. A heavily cratered landscape can preserve a record extending back billions of years. A smoother surface, with fewer visible scars, suggests that older terrain has been covered, altered, or erased. For Triton, the low crater count indicated that at least part of the visible surface may be geologically young compared with many other moons. The exact ages remain uncertain because only part of the world was imaged closely, and because crater rates in the distant solar system are difficult to reconstruct. But the broad message was clear. Triton had not simply frozen into its present form when the planets were young, and remained unchanged ever since something had renewed it. The strongest evidence arrived as dark marks near the southern polar cap. In several images, narrow columns appeared to rise above the surface before bending sideways into long trails. Voyager had seen plumes. The active sources were small compared with the Moon, but their presence changed the meaning of the entire landscape. Material was being lifted several miles upward through the thin atmosphere and then carried by winds. Dark streaks extended across the bright polar ice, recording both the eruptions and the direction of air moving above the ground. The favored explanation involves sunlight passing through a translucent layer of nitrogen ice. Darker material below absorbs some of that energy and warms slightly. Nitrogen can then turn directly from solid into gas. building pressure beneath the surface until it escapes through a vent. The rising gas carries dark particles with it, creating a plume before the atmosphere pushes the material downwind. The process is sometimes compared with a geyser, but no boiling water is required. It is a solar-driven eruption on a world where nitrogen plays roles that water and steam play elsewhere. Even the weakened sun can therefore shape Triton. Its energy arrives over broad seasonal timescales. A small amount of warming, repeated across years and decades, can move ice between the ground and atmosphere, change surface pressure, and awaken patches of the polar cap. Voyager also looked along the edge of the moon and detected a thin atmospheric haze. Layers appeared above the limb, suspended over the surface. These hazes likely form when sunlight alters methane and other molecules, creating more complex particles that settle gradually downward. The atmosphere was far too thin to hide the stars. It could not support clouds like those above oceans, but it was active enough to carry particles, build haze, and participate in a seasonal cycle. For the people receiving the images on Earth, Triton changed in a matter of days from an astronomical object into a place. A point discovered in a 19th century telescope became a world with geography. The observers who had measured its orbit without seeing its surface were connected across generations. To engineers and scientists watching new frames arrive from the edge of the solar system, each group worked with the light available to them. One detected motion beside Neptune. Another turned that faint motion into planes, caps, ridges and plumes. Yet the transformation was incomplete. Voyager photographed only the portion of Triton illuminated and visible during the flyby. Large regions remained unseen, and even the mapped areas were captured at different resolutions. No instrument could watch the seasons continue for years. No lander touched the nitrogen ice. No orbiter returned to see whether the plumes moved, stopped, or appeared somewhere new. The spacecraft passed closest on August 25th, 1989. Then Triton began to shrink again. Its surface narrowed from a landscape into a disk, from a disk into a point, and finally into the same distant light that had occupied human telescopes for generations. Voyager continued beyond Neptune, carrying its instruments toward interstellar space. The images remained behind. They showed that the captured moon had not become still. Its old orbit told of a violent beginning, while its young terrain and dark plumes suggested continuing change. Triton had lost its freedom around the sun, but not its capacity to transform. The event that bound Triton to Neptune cannot be observed directly. It happened so far in the past that no surface still carries a clear picture of the moment. What remains is a collection of consequences. An orbit running backward, a path that has become nearly circular, a moon system that looks disturbed, and a world whose interior may once have been heated far beyond what its distance from the sun would suggest. Taken together, those consequences point toward capture. A planet does not usually acquire a large moon by simply passing near it. Gravity can bend an approaching object's path, sometimes sharply, but a two-body encounter does not easily produce a permanent orbit. As Triton fell toward Neptune, it would have accelerated. Unless some of that energy was removed, it would have climbed away again after passing the planet, continuing into the outer solar system on a new course. For capture to last, something had to carry energy away. One possibility is that Triton struck another object or moved through a cloud of debris around the young Neptune. Friction, collision, or interaction with gas could have slowed it enough to remain. These ideas are not impossible, but each presents difficulties. A collision strong enough to remove the necessary energy might also have shattered Triton. A dense gas disk could have slowed it more gradually, but the conditions and timing would have needed to be unusually precise. The leading model instead begins with two icy worlds traveling together. binary objects are common in the distant population beyond Neptune. In such a pair, two bodies orbit a shared center, while the pair itself travels around the Sun. Pluto and Charon offer the most familiar large example. Though their relationship is unusually close and massive, many smaller Kuiper belt objects also have companions. Triton may once have belonged to a system like this. As the binary passed near Neptune, the planet's gravity would have pulled differently on each member. The one slightly closer to Neptune would have felt the stronger attraction. If the timing and geometry were favorable, the pair could have been torn apart. One object might then have carried away more energy than it arrived with, escaping into a wider orbit around the Sun. Triton, having lost that energy through the exchange, could have remained behind. Nothing in this model requires Neptune to touch Triton or pull it through a thick atmosphere. The capture would come from a three-body interaction, a transfer of motion through gravity. One world would be thrown outward, the other would be kept. The process is sometimes compared with separating two dancers by passing close to a much larger moving body. But the actual encounter would have been governed by speed, mass, angle, and distance, with only a limited range of paths leading to survival and capture. Too close, and Triton might have collided with Neptune or been broken apart by tidal forces. Too far, and the binary might have remained intact. Too fast, and both objects could have escaped. The fact that Triton exists where it does means the encounter fell somewhere inside that narrow region. At first, however, the captured orbit would have looked nothing like the one seen today. Triton now circles Neptune at a distance of roughly 355,000 kilometers. Its orbit is nearly circular. A newly captured body would more likely have followed a long ellipse, moving very close to Neptune at one end and far into the surrounding system at the other. It may also have had a different tilt from its present path. Each close passage would have raised tides. On Earth, the Moon pulls slightly more strongly on the near side of our planet than on the far side. This difference stretches the oceans and deforms the solid ground. Neptune would have done the same to Triton, but during the early captured orbit, the effect could have been much stronger. As Triton approached Neptune, the gravitational pull across its body would have increased. The Moon would have flexed. As it moved away, the deformation would have relaxed. Repeated again and again, this changing shape would have converted orbital energy into heat inside Triton. The process resembles bending a piece of material until it warms, though on a planetary scale the motion occurs throughout layers of ice and rock. Friction within those layers dissipates energy. The orbit loses some of its extreme shape. Over time, the distant part of the path moves inward, and the ellipse becomes more circular. This tidal evolution may have lasted hundreds of millions of years, depending on Triton's original orbit and the way its interior responded. During that period, the heating could have been intense enough to melt large amounts of internal ice. A world that began as a mixture of rock, water ice, and frozen volatiles may have separated into layers. Denser rock could have moved inward. Water and other materials could have formed a mantle above it. A temporary or persistent liquid layer may have developed beneath the surface. The capture, then, may have given Triton a second geological beginning. Before meeting Neptune, Triton was likely already an old body, formed in the distant solar system from materials left over after the Sun and planets emerged. Its original surface would have accumulated craters. Its interior would have cooled. Radioactive elements in the rocky portion would have supplied some heat, but the world's small size and great distance from the Sun would have encouraged gradual freezing. Neptune changed that path. The energy of capture did not remain only in the orbit. Through tides, some of it entered the Moon. Old terrain could have been fractured or erased. Ices could have melted, shifted, and frozen again. Materials from the interior may have risen toward the surface. The landscape Voyager later photographed may therefore preserve not the earliest Triton, but a world rebuilt after capture. The same encounter may also have transformed Neptune's earlier family of satellites. Before Triton arrived, Neptune probably possessed a more orderly system of moons. The major planets formed with disks of material around them, and those disks could produce satellites traveling in the same direction as the planet's rotation. Still has several large regular moons in such a pattern. Neptune may once have had something comparable, a newly captured Triton on a wide, eccentric, retrograde orbit would have crossed the region where those moons traveled. Gravitational encounters could have changed their paths. Some satellites may have collided with one another, others may have struck Triton or Neptune. Debris could have spread into temporary rings and later gathered into smaller moons. The irregular arrangement seen around Neptune today may be part of that aftermath. Inside Triton's orbit are several small moons with close, prograde paths. Proteus, the largest of them, is irregular in shape and heavily cratered. Far outside Triton are more distant irregular satellites on inclined and eccentric orbits. The entire system does not resemble a simple untouched disk of moons. Scientists cannot reconstruct every lost object or every collision. Too much time has passed, and later impacts have continued to modify the survivors. Yet, simulations suggest that Triton's capture could have destabilized a previous satellite system, leaving behind debris from which some of the inner moons later formed. In this view, Triton was not added gently to Neptune's surroundings. Its arrival reorganized them. Even Neptune may have been affected, though far less dramatically. The moon's mass is small compared with the planet, but tides work in both directions. Triton pulls on Neptune, raising a slight tidal bulge. Because Triton travels backward, that bulge does not push the moon outward, as Earth's tides gradually push our moon away. Instead, the interaction draws Triton inward. The change is extremely small from one orbit to the next. No telescope can watch the distance close perceptibly during a human lifetime, but the direction is steady. Triton is slowly losing orbital energy and moving closer to Neptune. Its distant past and distant future are therefore connected by the same tidal process. Soon after capture, tides shrank and rounded the orbit. Today they continue to reduce it, though at a much lower rate. Far ahead, perhaps billions of years from now, Triton may approach the distance where Neptune's tidal forces become stronger than the moon's own. Gravity can resist. That boundary is called the Roche limit. Inside it, an object held together mainly by gravity can be pulled apart. Triton would not fall intact into Neptune like a stone descending through air. It could fracture gradually, spreading material along its orbit. The fragments might collide, grind down, and form a broad ring around the planet. Neptune already has rings, but they are faint, narrow, and dark. A disrupted Triton could create something far more massive. For a time, the outer solar system might contain a ring system whose material once formed a rounded moon. This outcome remains remote and model-dependent. The exact timing depends on how quickly tides alter the orbit and how Triton's internal strength affects its breakup. Long before then, other changes in the solar system may matter. The Sun itself will evolve. Neptune's environment will not remain forever as it is now. Still, the inward migration is not speculation. It follows from the direction of Triton's orbit and the exchange of tidal energy between moon and planet. Earth's moon moves outward because it travels in the same direction that Earth rotates and because Earth spins faster than the moon orbits. The tidal bulge carried ahead by Earth's rotation transfers energy to the moon. Triton's retrograde motion reverses the relationship. Neptune's rotation carries its tidal response against Triton's orbital direction. Energy is removed from the moon's path rather than added to it. The difference is quiet, but permanent. For now, Triton remains safely outside the region where disruption would begin. Its orbit appears stable across any timescale relevant to human civilization. The Moon continues around Neptune every few days, presenting the same hemisphere to the planet and carrying its frozen plains through the long Neptunian seasons. Nothing visible from Earth announces that the orbit is shrinking. The change exists in the equations, in careful measurements, and in the accumulated effect of motion repeated without pause. A small exchange occurs each time Triton passes around Neptune. The planet turns, the Moon travels backward, tides rise within both bodies. A minute amount of energy becomes heat. The orbit contracts by an amount too small to notice. Then it happens again. The history of Triton is therefore not divided cleanly into capture, settlement, and stillness. Capture began a process that has never fully ended. The violent part passed long ago, but the gravitational relationship continues to evolve. That relationship may also help explain why the Moon is not entirely frozen inside. Even after the most intense early tidal heating faded, radioactive decay within Triton's rocky interior would have continued to release energy. Some models suggest that a layer of liquid water could still survive beneath the crust, especially if dissolved compounds lower its freezing point, and if the ice shell reduces heat loss. No direct observation has confirmed such an ocean. Voyager could not see beneath the surface, and Earth-based measurements cannot yet provide a complete answer. But Triton's size, composition, resurfaced terrain, and history of tidal heating make the possibility scientifically reasonable. If liquid remains, it would lie below layers of water ice and beneath the more volatile materials that shape the visible ground. Nitrogen frost, methane ice, and seasonal deposits would form only the uppermost skin. Far below, an ocean could occupy part of a world once warmed by the same capture that disturbed Neptune's moons. This possibility changes the meaning of Triton's frozen appearance. A surface temperature near absolute zero does not tell the whole thermal history of a planet or moon. Sunlight governs the upper layers, but gravity, radioactive decay, pressure, and insulation can create different conditions beneath them. A place that appears motionless from above may still preserve slow exchanges of heat within. Triton's backward orbit is therefore more than evidence of where it came from. It may be one reason the Moon became geologically renewed. It may have melted internal layers, erased older terrain, and helped create the conditions for later activity. The orbit is a record, an engine, and a prediction. It records the capture. It powered part of Triton's transformation, and it points toward a future in which Neptune may one day reclaim the Moon in another form. Beneath Triton's thin atmosphere lies a surface made from several kinds of ice, each responding differently to temperature, pressure, and time. The palest regions are not simply frozen water. Much of the visible ground is coated with nitrogen ice, mixed with smaller amounts of methane and carbon monoxide. These materials are volatile, meaning they can pass between solid and gas under conditions found on Triton. A slight seasonal change may be enough to move them from one region to another. Water ice forms a more durable foundation. At Triton's surface temperature, water is harder than many rocks on Earth. It does not melt under sunlight or soften during the local afternoon. It can fracture, fold, and deform over geological time, but it behaves as the structural crust beneath the shifting layers of nitrogen and methane. This creates a landscape with two different rhythms. The deeper crust changes through internal heat, tectonic stress, and the slow movement of solid ice. The upper surface responds more quickly to sunlight and season. Frost collects, retreats, darkens, and returns. Gas rises into the atmosphere and later settles somewhere else. The terrain photographed by Voyager appears to preserve both rhythms at once. Some areas are smooth and lightly cratered, suggesting that older features were covered or erased. Other regions contain long ridges and troughs, as though the crust had stretched and broken. There are broad depressions, irregular plains, and networks of fractures whose origins remain uncertain. Among the most recognizable regions is the so-called cantaloupe terrain. Its surface is divided into rounded cells, each separated by shallow grooves. Seen from above, the pattern resembles the skin of a melon, though each cell spans many kilometers. No close equivalent has been identified elsewhere in the solar system. Several processes might produce such a pattern. The crust may once have been warmer and more mobile, allowing blocks of ice to rise and sink. Large cells could have formed through solid-state convection, with warmer material moving upward and cooler material descending. Another possibility is that broad regions collapsed after internal layers shifted or melted. The available images cannot decide between these explanations. Voyager observed only one portion of Triton at useful resolution, and the lighting revealed shape more clearly in some places than others. Without global mapping, gravity measurements, or radar sounding, scientists must work backward from incomplete surface evidence. The pattern still tells us something important. Triton's crust has not always behaved as a rigid shell. It has been rearranged. In other areas, the surface seems to have been flooded by material that later froze. Broad plains contain low ridges and irregular boundaries that may mark separate episodes of flow. On a warmer planet, such features might suggest lava. On Triton, the flowing substance could have been water mixed with ammonia or another liquid or slushy combination released from below. This possible process is called cryovolcanism. Cryovolcanism does not mean ordinary molten rock erupting through an icy crust. It describes activity in which water, ammonia, methane, nitrogen, or other cold materials move in ways that resemble volcanic processes. They may rise through cracks, spread across the surface, build domes, or refill depressions. The word can make Triton sound more active than the evidence allows. Voyager did not record a large cryovolcanic eruption. No spacecraft has watched liquid or slush emerge from a vent. The interpretation comes from landforms that appear younger than their surroundings and from Triton's history of internal heating. Some features may have another origin. Ice can deform without becoming liquid. Frost can conceal older ground. Impacts can reshape a region, and sublimation can remove material from below the surface until the upper layer collapses. Triton offers several ways to make unfamiliar terrain. One of the most striking possibilities involves large circular depressions surrounded by smooth plains. These may be calderas, broad volcanic basins formed after subsurface material was removed. They may also be impact structures, softened or buried by later resurfacing. Without sharper images, both interpretations remain open. The uncertainty is not a weakness in the science. It is a faithful description of the distance between one encounter and a complete geological history. On Earth, geologists can walk across a field, examine crystals, measure layers, and compare rocks from neighboring regions. On Mars, orbiters have mapped most of the surface in detail, and rovers have studied selected sites from the ground. For Triton, the evidence arrived during a flyby, lasting only hours. Each image contains a large amount of information, but it also contains the limit of the viewing angle, the camera resolution, and the season in which it was taken. That season favored the southern hemisphere. During Voyager's passage, Triton's south polar region was tilted toward the sun. A bright cap covered a large part of the visible hemisphere. It was probably composed mainly of frozen nitrogen, with methane and other materials mixed through it. The cap was not uniform. Some places were bright and nearly unmarked. Others carried long dark streaks, often beginning at small points and extending in a common direction. These marks became evidence for winds moving through the thin atmosphere. Their sources were the plumes. Sunlight may penetrate a translucent sheet of nitrogen ice and warm, darker material below. Nitrogen at the base can then sublimate, changing directly from solid into gas. If the gas is trapped beneath the ice, pressure builds until it opens a path upward. Once released, the gas expands into the atmosphere and carries dark particles with it. Voyager images suggest that some columns rose several kilometers before bending into horizontal trails. The atmosphere, though thin, was dense enough to redirect the material. Particles then settled across the surface, leaving fans or streaks downwind. This explanation is often called the solid-state greenhouse model. The term does not describe greenhouse warming across the whole moon, to sunlight passing through a transparent or translucent ice layer and being absorbed beneath it. The warmed base becomes more active than the surface above, allowing pressure to develop where direct sunlight might otherwise seem too weak. The process depends on local conditions, the thickness and clarity of the ice matter. So does the darkness of the underlying material. A patch that absorbs more energy could activate, while a nearby patch remains dormant. The result may be a landscape where activity migrates with the seasons. Triton's seasonal cycle is prolonged because Neptune's year lasts more than a century and a half. As the angle of sunlight changes, nitrogen can leave one region and collect in another. Frost may build over decades. Atmospheric pressure may rise or fall. Surfaces can brighten after fresh deposition and darken when older material becomes exposed. Observations from Earth have suggested that Triton's atmosphere has changed since the Voyager encounter, though the exact pattern is difficult to measure and interpret. Stellar occultations, in which Triton passes in front of a distant star, allow astronomers to study how the star's light bends through the atmosphere. From these brief events, researchers can estimate pressure and temperature at different heights. The measurements do not provide a continuous record. Occultations are limited by geometry, weather, telescope access, and the brightness of the background star. Different analyses may also give slightly different results. Still, they show that Triton's atmosphere is not a fixed shell. It is part of the surface. Nitrogen molecules rise from the ice, travel above the ground, and later return. Methane enters the atmosphere in smaller amounts and reacts under ultraviolet sunlight. Those reactions help produce haze particles that can drift downward over time. The haze may contribute to the surface colors Voyager recorded. Triton is often described as pale or pinkish. Its coloration may come from mixtures of clean frost, darker geological material, and complex organic compounds produced when sunlight alters methane. Similar chemistry occurs on Pluto and several other cold bodies in the outer solar system. These compounds are sometimes called tholins. The word refers to laboratory-made mixtures created by exposing simple gases to radiation. It does not identify one exact molecule. On Triton, related materials may form in the atmosphere or on the surface, adding reddish or brownish tones to otherwise bright ice. A world dominated by frozen nitrogen is therefore not colorless. Its appearance records chemistry. Fresh frost can reflect sunlight strongly. Older deposits may darken as radiation changes them or as dust accumulates. Plumes can place dark particles across bright ground. Seasonal transport can cover one region and reveal another. The landscape seen at any moment may be temporary on geological timescales. Even impact craters can disappear. Triton travels through a region where collisions still occur, though less frequently than in the crowded early solar system. Every impact leaves a mark, but resurfacing can soften or erase it. A plane with few craters is not a place that avoided every collision. It may be a place where the evidence did not survive. This is one reason age estimates remain uncertain. Planetary scientists often count craters to compare the relative ages of surfaces. More craters usually indicate longer exposure. Fewer craters suggest younger terrain. But the method depends on knowing how often impacts occur and how well a surface preserves them. Triton's location complicates both questions. Its impact population may include objects from the distant solar system, debris associated with Neptune, and material placed onto altered orbits during the planet's early history. Its volatile surface can also bury or modify craters in ways that rocky ground cannot. Even so, the scarcity of obvious craters in Voyager's images is difficult to ignore. Large parts of the visible surface appear to have been renewed long after Triton formed. The renewal may have occurred during the period of strong tidal heating after capture. It may have continued through later episodes, driven by radioactive heat and the gradual freezing of an internal ocean. Seasonal activity continues at the surface, while deeper geological activity may now be rare or dormant. All three timescales can exist on the same moon. A plume can rise and fall within hours. A polar cap can shift over decades. A fractured plane can preserve changes that unfolded over millions of years. Beneath them, an ocean may take billions of years to freeze. From the surface, these layers of time would not announce themselves. The nitrogen frost would lie flat beneath a nearly black sky. Distant sunlight would cast long shadows across ridges and pits. Neptune would remain above the horizon, holding its position while the moon moved through another 6-day orbit. Yet every part of that view would be connected to motion. The frost would belong to a seasonal cycle. The haze would be descending. The dark streaks would record wind. The ridges would preserve stress. The smooth plains would suggest material once moved across them, and below the visible ground, heat would continue to find its way outward through a crust built from ice. The visible surface of Triton is only a thin expression of a much larger body. Nitrogen frost, methane ice, and carbon monoxide occupy the uppermost layers. Beneath them lies a shell dominated by water ice. Deeper still, scientists expect a rocky interior containing much of the moon's mass and nearly all of its long-lived radioactive elements. The exact arrangement is unknown. Voyager 2 measured Triton's size and helped refine its mass, allowing researchers to estimate its average density. That density is too high for Triton to be made only of ice. A substantial fraction must be rock or metal-rich material, mixed with the frozen compounds that formed far from the young sun. Soon after Triton formed, those ingredients may have been distributed throughout its interior. Heat from radioactive decay, collisions, and later tidal flexing could have allowed the moon to separate into layers. Dense rock would have moved inward. Water and lighter ices would have remained above it. This separation, known as differentiation, changes how a world cools. A rocky core can continue producing heat through the decay of uranium, thorium, and potassium. An outer ice shell can slow the escape of that energy, especially when it grows thick and develops layers with different physical properties. Triton's capture may have accelerated the entire process when its early orbit stretched far from Neptune and then returned close to the planet. The moon would have been repeatedly distorted by changing tides. Internal layers would have rubbed, bent, and shifted. Orbital energy would have become heat. Some models suggest that this heating may once have melted much of Triton's water ice. If so, a deep internal ocean could have formed beneath the outer shell. Rock might have settled toward the center while liquid water remained above it. As the orbit became circular and the strongest tidal heating declined, the ocean would have started to cool. The question is whether all of it froze. A layer of liquid water may still survive today. Scientists cannot yet confirm that it does, but the possibility is supported by several features of Triton's history and composition. The moon contains enough rock to provide continuing radioactive heat. Its ice shell may offer insulation. Compounds such as ammonia could lower the freezing temperature of water, and the early period of tidal heating may have left the interior much warmer than a body at Neptune's distance would otherwise become. The ocean, if present, would not resemble an open sea beneath a hollow roof. It would be compressed between layers, buried perhaps tens or hundreds of kilometers below the surface. Above it, water ice would form a thick crust. Below it, liquid might against high pressure ice or directly against rock, depending on Triton's temperature, composition, and internal structure. Each possibility leads to a different kind of world. If the ocean touches the rocky core, water could react chemically with minerals. Similar water-rock interactions occur on Earth's seafloor and may also occur inside moons such as Europa and Enceladus. These reactions can release heat and produce compounds that alter the chemistry of the water. For Triton, this remains a hypothesis. No plume has been sampled. No instrument has measured salts or complex molecules from the interior. The dark eruptions seen by Voyager are best explained by nitrogen gas moving through the polar surface, not by water rising from a deep ocean. The geysers do not prove an ocean. The young terrain does not prove one either. Both are pieces of a broader picture in which Triton has possessed enough energy to change after its formation. They show that the moon cannot be understood as a simple frozen remnant. But the source of each feature must be considered separately. Some resurfacing may have happened when the captured orbit was still producing intense tides. Some may have resulted from the slow freezing of internal water. Some may be caused by seasonal nitrogen moving across the upper few meters of the crust. A single landscape can record all of these processes without revealing which one happened most recently. The freezing of an ocean can itself drive geological activity. Water expands when it becomes ordinary ice. As an internal ocean loses heat and freezes from above, the growing shell can place stress on the layers around it. Cracks may open, blocks of crust may shift. Liquid mixed with ammonia or salts could be squeezed upward through fractures before freezing closer to the surface. At greater depth, pressure can create forms of ice denser than liquid water. These high-pressure phases do not behave like the familiar ice at Earth's surface. Depending on Triton's internal conditions, they could form a layer that separates the ocean from the rocky core. That separation would reduce direct chemical exchange between water and rock, but Triton may be small enough, and its ocean may be shallow enough that high-pressure ice is limited or absent. Current models do not all reach the same conclusion, because the result depends on quantities that have not been measured directly. The thickness of the crust is unknown. The concentration of ammonia is unknown. The present heat flow is unknown. Even the detailed distribution of rock and ice inside Triton must be inferred from bulk properties rather than mapped through gravity measurements. An orbiter could change much of this. As a spacecraft traveled repeatedly around Triton, tiny changes in its motion could reveal variations in the moon's gravity. Those variations would help scientists estimate how mass is distributed inside. A flexible ice shell, a dense core, and a buried liquid layer would each influence the gravitational field in different ways. A magnetometer might search for another clue. A salty ocean can conduct electricity as it moves through a changing magnetic environment. Electrical currents may be induced within it, creating a secondary magnetic signal. This method has provided evidence for oceans inside several moons of Jupiter. Triton's situation would be more complicated. Neptune's magnetic field is strongly tilted relative to the planet's rotation and offset from its center. Triton moves through a magnetic environment that changes as Neptune turns. In principle, this variation could help reveal an electrically conducting layer inside the moon. In practice, a spacecraft would need repeated, careful measurements to separate an induced signal from Neptune's own unusual field and from charged particles around the planet. Voyager passed Triton only once. It could not build the long record needed for that work. The Moon's surface may also respond to internal structure in ways that a future camera could detect. Long fractures, aligned ridges, or repeated patterns of deformation can preserve the direction of past stresses. Global mapping would show where the features seen in Voyager's limited images continue across the unseen hemisphere. If the crust once floated above liquid, large sections might have shifted independently. If the ocean froze unevenly, some regions might have expanded or contracted more than others. If tidal forces remain active at a low level, new fractures could form over long periods. Even now, Triton's present orbit is nearly circular, reducing the repeated squeezing that heats moons on eccentric paths. Io, Europa, and Enceladus retain significant tidal activity because their orbits and gravitational relationships continually change the stresses inside them. Triton does not experience the same kind of strong, rhythmic flexing today. Its orbit still carries a notable tilt relative to Neptune's equator, and the Moon remains part of a complex gravitational system. Yet most models suggest that radiogenic heat and the memory of earlier tidal heating are more important for any surviving ocean than intense present-day flexing. This makes Triton a different kind of ocean world candidate. Europa is heated by an ongoing orbital resonance. Enceladus releases material through active fractures near its south pole. Titan's interior is studied beneath a thick atmosphere and a surface rich in hydrocarbons. Triton offers a world whose possible ocean may be a remnant of capture preserved beneath a surface shaped by volatile seasons. Its liquid layer, if it remains, would be part of a history that began before Neptune claimed the Moon. Triton may have formed among objects that carried water, ammonia, methane, carbon monoxide, nitrogen-bearing compounds, and complex carbon chemistry into the outer solar system. Its original composition would have reflected the cold region where these materials could freeze and become incorporated into growing bodies. Capture then supplied new energy. Tides rearranged the interior. Heat allowed materials to separate and move. Cooling began again under different conditions. The Moon visible today may therefore contain two overlapping histories, one from its formation beyond Neptune, and another from its transformation after becoming a satellite. A buried ocean would connect them. Its water would come from the original body. Its warmth would partly reflect the captured orbit. Its chemistry would continue changing as the interior cooled. Even without liquid, Triton's deep ice could move. Solid water ice can flow when placed under pressure for long periods. The motion is far slower than any ocean current, but across millions of years it can transport heat and reshape a crust from below. Warmer ice may rise while colder ice descends, creating broad convection cells. This process could help explain the repeated patterns of the cantaloupe terrain. It could also renew the surface without requiring large volumes of liquid to erupt. A slowly overturning ice shell might raise some regions, lower others, and fracture the upper crust as material circulates beneath it. The cellular pattern seen by Voyager may be the frozen surface expression of such movement, or it may record a process no longer active. Without another mission, time remains difficult to separate from structure. A feature may look young because it formed recently, or because the outer solar system supplies impacts so slowly that even an old plane retains few craters. A fracture may have opened during early tidal heating, or much later as the ocean froze. The surface gives clues, but not dates precise enough to settle the sequence. For now, Triton's interior exists mainly in models. Researchers begin with its diameter, mass, density, surface composition, orbital history, and likely formation materials. They calculate how quickly heat escapes, how ice behaves under pressure, how much radioactive energy the rocky fraction can produce, and how ammonia or salts change the freezing point. Different assumptions produce different interiors. In one, the ocean has already frozen. In another, a thin layer remains. In another, tens of kilometers of liquid still separate the crust from the deeper interior. Science does not yet choose among them with confidence. But each model agrees on one broader point. Triton has a depth that cannot be read from its pale surface alone. The frost seen by Voyager may be only the seasonal covering of a water ice shell. The shell may rest above a hidden layer that has survived since the era of capture. Below that, a rocky core continues releasing small amounts of heat into the moon. From a resting place on Earth, Triton is too distant to see without a telescope. Even through powerful instruments, it remains a tiny point beside Neptune. Yet inside that point, ice may be convecting, water may be cooling, minerals may be reacting, and heat may still be crossing upward through layers formed billions of years ago. The surface receives only a faint share of sunlight. The interior keeps another record of energy entirely. Triton's surface is shaped by Neptune, but much of its identity belongs to a region farther away. Beyond Neptune lies a broad population of icy bodies left from the formation of the solar system. Some travel on nearly circular paths. Others follow tilted or elongated orbits. A few are large enough for their own gravity to pull them into rounded worlds. Triton was probably once one of them. Its size, density, and surface composition place it close to the family of objects now associated with the Kuiper belt. The resemblance is clearest when Triton is compared with Pluto. The two worlds are not twins, but they share a recognizable set of materials. Both have surfaces containing nitrogen, methane, carbon monoxide, and water ice. Both possess thin atmospheres dominated by nitrogen. Both display landscapes that can change as volatile ices move between ground and sky. Their diameters are also similar. Triton is somewhat larger than Pluto, though the difference is modest on a planetary scale. Each is large enough to be rounded, internally layered, and geologically complicated. Each formed in the cold outer reaches of the solar system, where compounds that remain gases closer to the sun could freeze and become part of solid worlds. Yet their later histories separated them. Pluto continued orbiting the sun. Triton became a moon. That single difference altered almost everything that followed. Pluto remained part of a distant population whose members interact only weakly with the giant planets most of the time. Triton passed close enough to Neptune for gravity to take control of its path. The capture removed it from an independent solar orbit and placed it inside the environment of a massive planet. From that point onward, Triton experienced tides, heating, orbital evolution, and possible collisions with older Neptunian moons. Pluto did not. This makes the comparison valuable because it offers a kind of natural experiment. Two broadly similar icy bodies began with related ingredients. One remained free, the other was captured and transformed. Their present surfaces preserve the difference. Pluto's most familiar feature is a bright, heart-shaped region containing a vast basin filled with nitrogen ice. Within that basin, the ice appears to circulate slowly, rising and sinking in broad cells. Mountains made from water ice stand along parts of its boundary. Triton also has bright nitrogen-rich terrain and patterns that may reflect movement within an icy crust. It has smooth plains, ridges, depressions, and cellular landscapes, but its geology carries the added influence of a violent capture and prolonged tidal heating. Similar materials do not produce identical worlds. The outcome depends on orbit, internal structure, sunlight, pressure, and history. Even the atmospheres illustrate this. Both Pluto and Triton are cold enough for nitrogen to freeze onto the surface. When sunlight warms a region, some of that ice can become gas. When conditions cool, the gas can return to the ground. This creates atmospheres that are connected directly to seasonal frost. They are not permanent oceans of air like Earth's atmosphere. They are more like temporary extensions of the surface, built and reduced as volatile materials migrate across the world. Pluto's distance from the Sun considerably during its elongated orbit. That variation affects how strongly its surface is heated over the course of its year. Triton remains at almost the same solar distance as Neptune, but its unusual orbital tilt creates another form of seasonal change. Different regions receive changing patterns of sunlight as Neptune travels around the Sun. In both places, the seasons unfold across decades. A human observer could spend an entire lifetime watching only part of one seasonal transition. That duration changes the meaning of weather. A frost deposit might remain for years. A polar cap could shift over generations. Atmospheric pressure might rise or fall so gradually that the change would be visible only through measurements separated by long intervals. The surface may appear fixed during a single visit, while still belonging to an active cycle. This was one of the lessons of the two spacecraft's encounters. Voyager 2 passed Triton in 1989. New Horizons passed Pluto in 2015. The missions were separated by more than a quarter century, yet both encountered worlds that had been reduced to distant points for most of astronomical history. In each case, a brief flyby revealed plains, haze, layered terrain, and signs of change. Neither spacecraft could remain. The images arrived during narrow windows, each showing one world under one particular season and one particular angle of sunlight. The resemblance between Triton and Pluto became clearer, but so did the differences. Pluto has a large companion, and Charon, and several smaller moons. Pluto and Charon orbit a shared point located outside Pluto itself, creating a paired sab, unlike Triton's relationship with Neptune. Triton, by contrast, is tiny compared with the planet it circles. Neptune dominates the system completely. The moon's path, rotation, and long-term future are governed by that larger body. Triton may once have belonged to a binary pair, much like those still found beyond Neptune. If the capture model is correct, the missing companion was not destroyed necessarily. It may have been expelled during the encounter, leaving Triton behind. Somewhere in the outer solar system, an icy body may still travel on an orbit shaped by the same gravitational exchange. There is no practical way to identify it now. Billions of years of planetary motion would have erased the connection from any simple comparison of present paths. The former companion might have been scattered far outward, placed on a different orbit, or lost from the solar system entirely. Only Triton's capture remains visible. Its reversed motion acts as the lasting clue. The broader Kuiper belt helps place that event in context. The region beyond Neptune is not a thin ring with a sharp outer wall. It contains several orbital populations shaped by the migration of the giant planets during the early solar system. Neptune itself did not form exactly where it travels today. Models of planetary formations suggest that the giant planets changed their positions while interacting with a wide disk of smaller bodies. As they moved, they scattered some objects inward, some outward, and some into stable orbital relationships. Neptune left a strong pattern in the distant population. Pluto belongs to a group of objects whose orbital periods are linked with Neptune's. For every 3 trips Neptune makes around the Sun, Pluto completes 2. This resonance prevents repeated close encounters, even though Pluto's orbit crosses inside Neptune's average distance from the Sun. Other distant objects occupy different resonances or move through more scattered paths. Triton may have encountered Neptune during this unsettled age, when the outer solar system contained many more bodies and the planets were still shaping the architecture around them. The capture may therefore be part of a much larger rearrangement. Neptune did not simply receive a moon. It removed one world from the distant disk, disturbed its own satellite system, and preserved a sample of the early outer solar system close to the planet. Triton is now easier to reach than many comparable Kuiper Belt objects, though it remains enormously distant from Earth. A mission to Neptune could study a captured body in detail, while also examining the planet, its rings, magnetic field, and smaller moons. The Moon offers access to material formed in the same broad region as Pluto and other distant worlds, but altered by a history none of them share in quite the same way. Its surface chemistry may preserve traces of that origin. Methane and nitrogen dominate much of the visible volatile cycle, while water ice forms the deeper crust. Carbon-bearing compounds created by radiation may settle from the atmosphere or accumulate on the ground. Over long periods, cosmic rays and ultraviolet sunlight can break simple molecules apart and allow their fragments to recombine. The resulting chemistry produces darker, more complex material. These substances do not demonstrate biology. They show that organic chemistry can develop in cold environments without life, using simple carbon-bearing molecules and energy from radiation. Similar processes occur across the outer solar system, on Pluto, Titan, comets, and other icy bodies. Triton's capture then placed this chemistry inside Neptune's magnetic environment. Charged particles, sunlight, seasonal frost, and possible internal activity all act on the same surface. A molecule formed in the atmosphere may settle onto nitrogen ice. Later, the ice may sublimate. The molecule may remain behind, become buried, or be carried upward in a plume. Over time, the visible colors and textures become a record of repeated sorting. Bright frost covers darker ground. Dark particles fall across pale polar deposits. Radiation alters exposed material. New frost hides the older layer. The process may continue through season after season, each one lasting decades. There is a calm persistence to this cycle. The changes are real, but they do not need to happen quickly. A surface can remain recognizable for a human lifetime and still be temporary from the Moon's perspective. This is one reason Triton feels both preserved and transformed. Its materials belong to the solar system's distant beginning. Its orbit records a later capture. Its terrain may preserve episodes of tidal heating. Its atmosphere responds to sunlight arriving now. Several ages occupy the same place. The world that formed beyond Neptune has not vanished. It remains in the composition of the ice, the density of the interior, and the chemistry of the surface. But it can no longer be separated from the planet above it. Neptune changed Triton's path, warmed its interior, altered its neighboring moons, and began a tidal relationship that continues today. Triton, in return, gives Neptune something no other giant planet possesses: a large captured moon, carrying the character of the distant solar system into a close planetary orbit. It is both visitor and satellite, both relic and active world, both a member of Neptune's family and evidence that the family was once very different. Far beyond the bright planets, where sunlight reaches the ground with little warmth, Triton continues around Neptune in reverse. Beneath its frost lies the memory of another orbit, one that once carried it freely around the sun. The next clear answer about Triton will probably arrive the same way the first one did, through a spacecraft crossing billions of miles of space. No mission has returned since Voyager 2. Earth-based telescopes have improved greatly, and observatories in space can study Triton's atmosphere, surface composition, and seasonal changes. Yet the Moon remains too distant for even the best remote instruments to resolve the details needed to reconstruct its geology or determine what lies below the crust. Telescope can measure the light reflected from nitrogen ice. It cannot look closely into a fracture. It can detect changes in atmospheric pressure. It cannot watch a plume rise from its source. It can identify broad chemical signatures. It cannot measure the thickness of an ice shell or determine whether liquid water survives beneath it. Those questions require proximity. Reaching Neptune is a long exercise in celestial timing. A spacecraft cannot travel there by pointing outward and moving in a straight line. Its route each must be designed around the changing positions of the planets, the energy available from its launch vehicle, and the gravitational assistance that other worlds can provide. Jupiter is often the most useful partner. A spacecraft passing near the giant planet can exchange momentum through gravity, leaving the encounter with greater speed relative to the Sun. This maneuver does not give the spacecraft free energy. Jupiter loses an immeasurably small fraction of its own orbital motion, while the much smaller machine gains enough speed to shorten years of travel. Even with such assistance, a Neptune journey may occupy a large part of a human career. Engineers who begin designing the mission may retire before all its data has returned. Children alive at launch may be adults when the spacecraft reaches Triton. Instruments must survive years of radiation, cold, vibration, and inactivity before performing the work for which they were built. That delay is part of exploring the outer solar system. Mars missions can be designed, launched, and completed within a relatively compact span. A Neptune mission belongs to another pace. Its planning extends across administrations and generations of scientists. Its success depends on decisions made many years before the target fills a camera frame. The spacecraft would also have to work in weak sunlight. Solar panels are highly effective near Earth and can operate as far away as Jupiter with careful design. Near Neptune, sunlight is so reduced that a large array would produce relatively little power while adding mass and complexity. Most serious mission concepts therefore rely on radioisotope systems, which turn heat from the natural decay of plutonium into electricity. That power source would operate continuously through the long cruise and the distant encounter. It would run heaters, computers, instruments, transmitters, and the small mechanical systems that keep the spacecraft pointed correctly. The available electrical power would be limited, so observations would have to be scheduled carefully. Some instruments might work while others rested. Data would be stored on board and transmitted gradually. Communication would move no faster than light. Depending on the positions of Earth and Neptune, a radio signal can require more than 4 hours to cross the distance in one direction. A command sent in the morning might not arrive until later in the day. Confirmation that it had been received would require another journey back. There could be no direct steering through a close encounter. Every important movement would be prepared in advance. The spacecraft would carry out instructions on its own, checking its orientation, protecting itself from faults, and deciding when to enter a safe mode if something went wrong. The first choice would be whether to fly past Triton or remain in the Neptune system. A flyby could be lighter and less costly. It would approach rapidly, gather observations during a concentrated period, and continue outward. With modern cameras and spectrometers, even a brief passage could map regions. Voyager never saw compare the two hemispheres, search for new plumes, and major changes accumulated since 1989. One proposed concept called Triton was designed around such an encounter. It would have used a carefully chosen path to pass near Triton, examine its surface, sample the space around it, and investigate whether the moon might contain a hidden ocean. The concept was studied but did not become a flight mission. Its scientific goals remain relevant. Has the surface changed since Voyager? Are the dark polar fans renewed each season? Does the atmosphere possess an ionosphere more active than expected? Is the crust thin enough to reveal signs of an internal liquid layer? A flyby could address parts of each question, but it would again provide only a narrow interval of observation. An orbiter would offer a deeper record. A spacecraft placed around Neptune could encounter Triton repeatedly, using the moon's gravity to reshape its path and gradually examine different regions. Each passage could occur under a different viewing angle, lighting condition, and magnetic environment. Over months or years, the mission could build a global map. It could watch for surface changes. It could measure the atmosphere during different portions of Triton's orbit. It could observe Neptune, its rings, and its smaller moons, while returning again and again to the captured satellite. Mission studies, such as Neptune Odyssey, have examined this broader approach. In those designs, Triton is not treated as a brief stop beside Neptune. It becomes a central part of an extended tour through the system. The challenge is slowing down. A spacecraft arriving at Neptune carries tremendous speed. To enter orbit, it must remove enough energy to avoid escaping again. That can require a large engine burn, a carefully planned passage through the upper atmosphere, repeated gravitational encounters, or some combination of these methods. Every solution carries risk and mass. Fuel used for braking cannot be used later. A heat shield adds weight. A trajectory that saves energy may require more time. The engineering becomes a negotiation between what the spacecraft can carry and what the science requires. Once near Triton, a camera could begin by finishing the map that Voyager left incomplete. More than half the moon was poorly seen during the 1989 encounter. Some regions were hidden in darkness. Others appeared at low resolution or near the edge of the visible disk, where shapes were distorted by perspective. Modern imaging could reveal whether the cantaloupe terrain extends across the globe or belongs to a limited region. It could identify small craters, narrow fractures, layered deposits, and subtle changes in elevation. Stereo images taken from different angles could produce topographic maps. A thermal instrument could search for places slightly warmer than their surroundings. At Triton's temperature, even a small difference would matter. A warmer patch might indicate recent deposition, sunlight absorbed beneath translucent ice, or heat leaking from below. No single warm area would prove present geological activity, but repeated measurements could distinguish temporary solar effects from persistent internal sources. Spectrometers would separate the surface into chemical regions. They could map nitrogen, methane, carbon monoxide, carbon dioxide, water ice, and more complex compounds. By comparing composition with geology, scientists could learn whether certain materials emerged from below, settled from the atmosphere, or migrated across the surface with the seasons. Ultraviolet observations could examine the upper atmosphere and ionosphere. Triton's thin gases interact with sunlight, Neptune's magnetosphere, and charged particles moving through the system. These interactions may remove atmospheric molecules, change their chemistry, and create electrical layers far above the frost. A mass spectrometer passing through the upper atmosphere could identify molecules directly. If active plumes were found and the trajectory allowed it, the spacecraft might cross through material released from the surface. That sample would have to be interpreted carefully. A nitrogen-driven plume may carry particles from only the shallow crust, not from a buried ocean. Still, those grains could reveal surface chemistry at a level impossible from remote sensing alone. Gravity measurements would reach deeper. As the spacecraft passed Triton, the moon's mass would alter the radio signal received on Earth. Tiny changes in frequency could show how gravity varies from place to place. A differentiated interior, a thick ice shell, and a hidden ocean would each influence the spacecraft differently. A magnetometer could search for the electrical response of conductive liquid beneath the crust. The result would not be simple. Neptune's magnetic field is tilted, offset, and continually changing around Triton. But that complexity may provide the variation needed to induce a detectable signal inside a salty ocean. Repeated passes would be critical. One measurement could be ambiguous. A pattern returning under different conditions would be harder to dismiss. A lander would offer another level of detail, though reaching the ground would introduce new problems. Triton has almost no atmosphere to slow a descending spacecraft. Parachutes would provide little help. Rockets would have to control most of the descent. The surface might be firm water ice, loose nitrogen frost, or layered material whose strength changes over short distances. A safe landing site would need enough light for imaging, enough visibility for communication, and terrain smooth enough to avoid damaging the craft. Once down, a lander could measure pressure, wind, temperature, and surface chemistry directly. It could listen for movements within the ice. It might watch frost accumulate or disappear around its feet. A more ambitious machine could drill, hop, or travel between sites. Concept studies have imagined vehicles using Triton's nitrogen as a resource, collecting surface material and heating it to create propellant for repeated movement. Such ideas remain exploratory. They show what might someday be possible, not what has been approved for flight. The first return will probably be simpler. It may be a fast flyby carrying modern instruments. It may be a Neptune orbiter designed to study the whole system. It may emerge from a mission class not yet defined. Whatever form it takes, the spacecraft will arrive with a list of questions shaped by one earlier encounter. William Lassell saw a moving point in 1846. Voyager turned that point into a landscape in 1989. A future mission could turn the landscape into a history. Between those moments lies a chain of observation handed from one generation to the next. The instruments change, the questions become more precise. The Moon continues around Neptune, following the same backward orbit, while people on a small inner planet prepare to look again. When the next camera approaches, Triton will not need to reveal everything at once. A changed plume, a new fracture, a gravitational variation, or a faint magnetic response may be enough to open the next part of its story. Triton continues to circle Neptune beyond the range of ordinary sight. From Earth, the Moon remains hidden beside a planet that itself appears only as a small blue point through most telescopes. The planes seen by Voyager cannot be resolved from a backyard observatory. The dark fans cannot be followed across the polar cap. Any haze above the horizon is far too thin and far too distant to be seen directly. Yet the world is there in full. Its nitrogen frost is exposed to another weak sunrise. Methane molecules rise into the atmosphere. Haze particles settle toward the surface. Somewhere along the bright southern terrain, old streaks remain as records of winds that passed decades ago. The changes may be small. A layer of frost may grow slightly thicker. A dark patch may become covered. Atmospheric pressure may shift as sunlight reaches a different latitude. No one needs to witness these movements for them to continue. Triton's present has always unfolded beyond immediate observation. It completed millions of orbits before William Lassell recognized it as a moon. It crossed season after season before Voyager arrived. It has continued through thousands of six-day circuits since the spacecraft passed it, carrying the photographed hemisphere away from Earth and bringing unseen regions into sunlight. The single encounter did not interrupt the Moon's history. It entered it briefly. That brief visit left us with a world more complicated than the distant point that came before. Triton became a place where gases freeze onto the ground, where sunlight can drive dark material upward through a polar sheet, and where landscapes may have been renewed long after the Moon first formed. It also became evidence of an event that changed an entire planetary system. The backward orbit is still the clearest surviving trace. Neptune turns beneath its clouds while Triton travels against that rotation. Every circuit repeats the geometry of capture, preserving a direction established billions of years ago. The original encounter is gone. The former companion, if there was one, is gone. The older moons that may have occupied Triton's path are gone or transformed, but the motion remains. This is one of the quiet strengths of orbital science. A path can preserve history after surfaces have been erased. Craters may be buried, ice may flow across fractures, atmospheres may collapse and return. Yet an unusual orbit can hold the outline of an ancient event in its speed, tilt, and direction. Triton carries that outline around Neptune again and again. Its future is also written into the same motion. The moon is moving inward, though so slowly that no human observer will watch a noticeable change. The orbit will remain stable through civilizations, languages, and every lifetime now unfolding on Earth. Only over immense spans does the destination become clear. Neptune's tides will continue to take energy from Triton's path. The moon will move closer. The planet will fill more of its sky. Far ahead, if the present evolution continues, the distance between them may become too small for Triton to remain whole. There is no Sun waiting nearby. The moon is not approaching destruction on any scale that belongs to human concern. Its inward movement is a deep time process, measured across billions of years and shaped by conditions that future solar evolution may alter. Still, the possibility gives Triton's story a long arc. It may have begun as an independent world orbiting the Sun. Neptune captured it, heated it, and turned it into a moon. In the distant future, the same planet may pull it apart and spread its ice and rock into a ring. A rounded world could become a disk of fragments. The ring might then change again. Particles could collide, fall toward Neptune, or gather into new small moons. Matter that once formed one captured body could become part of a different system of orbits. There is no permanent final arrangement in that sequence. There is only gravity continuing to redistribute what it holds. For now, Triton remains intact. Its shape is maintained by its own gravity. Its crust supports ridges, plains, pits, and polar deposits. Its thin atmosphere continues to rise from the surface, rather than existing separately from it. Below, the water ice shell may be still, or it may be moving by amounts too small to reach the surface during any short observation. A buried ocean may remain between the crust and deeper layers, or it may have frozen, leaving behind structures that only a future mission could recognize. The uncertainty does not make Triton empty. It gives form to the next questions. How recently was the surface renewed? Do the plumes return under changing sunlight? How thick is the crust? Does the interior still contain liquid water? Which regions were hidden from Voyager, and what history is preserved there? Each question belongs to evidence that has not yet arrived. Somewhere on Earth, instruments capable of answering them may already exist in early designs. Some may not be invented for years. The people who eventually use them may study images taken before they were born and build a mission whose results will reach another generation. This has always been part of looking outward. The distance to Triton is not only spatial, it is institutional, technological, and human. It requires knowledge to pass through many hands without losing the patience needed to continue. Lassells shaped mirrors and watched for movement beside Neptune. Voyager's engineers built a machine that survived the crossing. Scientists later returned to the old data with new models, asking questions the original teams could not fully answer. The next observers will inherit all of it. They may see a changed polar cap. They may discover unfamiliar terrain on the far hemisphere. They may find no active plumes at all. They may detect an ocean or learn that the moon has frozen more completely than expected. Whatever the result, Triton will not become less interesting by being measured more carefully. Its value does not depend on one dramatic discovery. It lies in the relationship between origin, capture, heat, ice, atmosphere, and time. It is a record of how a world can be removed from one path and given another. It shows that becoming a moon can alter an interior as well as an orbit. It reminds us that cold surfaces can remain active through chemistry, sunlight, and buried heat. And it places those ideas in a landscape that has been seen only once from nearby. Far beyond us, Neptune continues along its long year. The sun appears small from there, but its light still reaches Triton. It enters the thin haze, touches the nitrogen ice, and leaves faint shadows along terrain whose full shape has never been mapped. The moon continues backward beneath the blue planet. Its past remains in the orbit. Its future waits closer to Neptune. And beneath the frost, the captured world keeps turning.